What is the ultimate goal of sterilization? It's simple: to ensure that every surface of an instrument or a pharmaceutical product reaches a sterile state, meaning no viable microorganisms remain. Every living thing is killed. The definition of sterile is actually quite straightforward. But if you read CSSD-related literature or standards, you'll definitely come across another concept, the Sterility Assurance Level, SAL. And it always appears together with a specific number, 10 to the power of minus 6, or 1 in a million. What does this SAL actually mean? In our last video, we learned about the D-value of a microorganism, a measure of its resistance to sterilization. We used an example to show how the number of spores decreases logarithmically during the process. For every fixed period of sterilization time, the population drops to 1/10 of what it was before. By the end of our example, the count went from initially 1 million spores down to just 1. Now, here's a question. If we put that last remaining spore back into the sterilizer and run exactly the same 121 degrees 2 minutes cycle again, how many would be left afterward? If we follow the same calculation pattern, the answer seems very clear. There should be only 0.1 spores left, right? But that is impossible. A spore is already a single-cell organism and cannot be divided into smaller units, just like you can't have 0.3 humans. So how do we interpret this in 0.1? Let's change the example. We still have the same sterilizer running at 121 degrees, but this time, instead of just putting in spores, we will load 10 instrument packs inside. Let's assume that each pack carries only one viable spore. So there are 10 spores in total. Place all 10 packs into a sterilizer and run this 121 2-minute cycle. After it finishes, we immediately open the door. Now think about it. How many spores are still alive inside the chamber at this very moment? Using the same calculation, we know the answer is 1 spore remains, right? But now here comes the next question. On which of the 10 packs is that last spore? No one knows, because the probability of that last spore surviving on any given pack is exactly the same, and that probability is 0.1. So when our mathematical calculation of spore count gives us a number less than 1, let's say 0 something or 0.00 something, it no longer represents the actual number of surviving spores. Instead, it represents the probability that a single item might still be contaminated. If the probability of an instrument being contaminated is 0.1 or 1 in 10, could we use it on a patient? Of course not. That would be like saying in every 10 surgeries, one patient receives a contaminated instrument. I certainly wouldn't want surgery at that hospital. So we need to lower the probability that an instrument remains non-sterile. How do we do that? Simple, by extending the sterilization time a bit longer. As we extend the time, the probability keeps dropping from 0.1 to 0.01 to 0.00001 and even lower. But will it ever hit 0? Never. It can become infinitely small, approaching 0, but it will never actually equal 0. So what do? We can't sterilize endlessly. We need to pick a point to stop it, and at that chosen point, the probability of an instrument still being contaminated must be low enough that, for all practical purposes, it is as good as 0. But what a probability is acceptable? The global requirements for surgical instruments is the same. 10 to the power of minus 6, or 1 in a million. 10 to the minus 6 is a mathematical threshold for releasing an instrument as sterile. If the contamination probability falls below this value, we consider that instrument mathematically sterile. Now let's come back to the concept of SAL. All these probabilities are sterility assurance levels. They're just different levels, and the minimum level we are required to achieve is 1 in a million. Going lower is always fine, but we must at least reach 1 in a million.